Hello everyone, welcome to Unravel Logic channel. In today's video, we will cover the concept of correlation. To understand this, you need to know about covariance. I have covered it in one of my previous videos. So, as usual, let us start with the formal definition first. So, correlation is defined as a unitless, normalized measure of the linear relationship between two variables. Unitless, normalized measure of linear relationship between two variables. These two words are very important: unitless and normalized. We'll understand these two words with the help of the mathematical formula. For now, just understand the formal definition. So it is a measure of it is a unitless and normalized measure of linear relationship between two variables. Okay. Now let us understand this formal definition with the help of the mathematical formula. So the formula builds over the concept of covariance, which we have already seen in the previous video. So let me write the formula for covariance first, and then we'll build the formula for correlation using the formula of covariance. Okay. So you see, this is the formula for covariance. We write it as COV x comma y equals 1 over n summation of xi minus x bar times yi minus y bar from I equals to 1 to n. Okay. And needless to say, we have already seen that this stands for x bar, which is nothing but mean of x, and this is similarly, this is y bar, mean of y. Okay. Now let us build the formula for correlation using this. So correlation equals covariance of x comma y, which is nothing but this whole formula over the product of the standard deviation of x and the standard deviation of y. Now, just to recap a bit, if you recall, the formula for standard deviation goes something like this. So this is square root of 1 over n summation from I equals 1 to n xi minus x bar whole square. Okay. So this is the formula for standard deviation. This is for x. Same thing would be for y. We just need to replace x from y. Okay. So just let me mark it down anyways. So this is standard deviation of x. This is standard deviation of y, and we are looking at the product of standard deviation of x and y. So now see, I mean, it's easy to see this formula and understand what it is doing mathematically, but we need to understand why the formula is the way it is. Why did we divide the covariance by the product of standard deviation of x and standard deviation of y? Okay, so what we really need to understand is why this. Okay, so the reason is that there was one problem when it comes to covariance. When we studied covariance, there was one problem. It was related to the units of the two variables and the covariance itself. So if we take an example, to explain this, okay, x equal to height in centimeters and y equals to weight in kg. So for example, let's suppose that we are trying to understand the relationship between the height and weight, okay, whereas height is in centimeters and weight is in kilograms. Okay, so the unit of covariance would be, in case of this example, would be centimeters kg. Okay, product of centimeters and kg, because this is centimeters, this is kilograms, so this would be centimeters and kg. Okay, all right, so you quickly realize that centimeter kg is not something that means something. Okay, so this does not mean anything. What does this tell you? Nothing. Okay, nothing meaningful basically. Okay, now when it comes to magnitude of covariance, for example, if the value was, let's say, 10 centimeter kg, we would understand that since this is a positive value, the relationship is positive, right? And when height is increasing, the weight is increasing as well to some extent, right? But it doesn't really tell us, if even if this was like 20 centimeters kg, you would understand that this is positive and there is some relationship between height and weight. But this, apart from the sign component, right, the magnitude and the unit doesn't really matter. Okay, it doesn't tell you anything. So that was the problem with covariance. Okay, now furthermore, if we multiply the x and y by some constants, for example, if I multiply the height by a constant of 5, okay, and if I multiply the weight by a constant of 3, so what effectively happens is that the covariance gets multiplied by their product, which is 15. Okay, so whatever was the original covariance, let's say it was 10, it gets multiplied by 15 and the unit still remains the same, which is like 10 times 15 centimeter kg. Okay, so it would be effectively, it would be 150 centimeter kg, right? And just like we discussed here, only the sign matters, the magnitude wouldn't really matter here. Okay, so this was the problem with covariance. Now how correlation solves it is what we'll see. Okay, so what if we could make covariance unitless and normalized? So let us understand what we mean by these two words now, unitless and normalized. So the way we make it unitless is to divide by the product of standard deviations. Okay, so dividing by the product of standard deviations serves two purposes. One is to make it unitless, one is to make it normalized. First, let us understand how this division makes it unitless. So let us understand it using a mathematical example wherein we have these two quantities, two variables, x and y. Okay, so we have x and then we have y. So x has two values, 50 and 30. We are taking a very simple numerical example. Okay, and then y has values 150, 130. Let's say that x is height and y is weight. Okay, so x bar would be 40. Okay, and then y bar would be 140. Okay, right, so I have pre-calculated, so I'm just noting down the numbers, but you can go ahead and calculate, you would get the same values. Okay, so 40, 140, so this is and this. Okay, Now if you calculate covariance, okay, and let's say the unit is this is this is height in centimeters and this is weight in kilograms. Okay, so now if you calculate covariance first, okay, so covariance of x comma y, this would be what, somewhat around 200 by 2, so it would be 100. Okay, and the units would be what, centimeter kg. Okay, now this is as usual till now. Okay, the way we calculate covariance, nothing extra here. Okay, now the formula of correlation tells us that we need to divide by the product of standard deviations. Okay, so what we need to do is we need to keep it this way, 1 by 2 times 200. Okay, and then the standard deviation is something like this. So I will calculate the standard deviation here of x. So this is 1 by 2 and we are going by this formula. Okay, this formula of a standard deviation, so which is 1 by n then summation of xi minus x bar whole square. Okay, so that would be 10 square plus 10 square. Okay, and then for y, okay, so it would be the same thing for y as well, because the difference from the mean is 10. Okay, it is 10 here, so basically like 50 minus 40 and then 30 minus 40, right? This would be minus 10 actually. Okay, and 10 square minus 10 square. Okay, because this would be negative 10 and this would be positive 10. Okay, and similarly it would be here as well, so positive 10 and then negative 10. Okay, same thing. So yeah, right, so something like this, something like this. Okay, and you would get 1 by 2 times 200 over 1 by 2 times 100 plus 100. Okay, and because if you do these square roots and everything, it would be the same thing. Okay, so yeah, correct. Okay, so what this would be, so 10 square 100 plus minus 10 square 100, so 200, and then divide by 200, square root of 100 is 10, so this would solve something like this. This would be 10, and then again this would be 10. Okay, and then yeah, 100, right? So ultimately this would be 100, and if you take the factor of half out, then you wouldn't simply do this, so you would keep it like 200 and then times 200, right? This would be 400, and then you would get 1 by 2 times 200. Okay, I hope you understand that. It's simple mathematics, you can calculate it yourselves. I will just skip it, right? So this is 1 by 2 times 200, and then this would be 1 by 2 times 200, right? And these, everything would cancel out, so you would get basically 1, right? So this was centimeter kilograms, and this whole term, right, this whole term basically, this was also centimeter kilograms, right? So it would be 1 by 1 centimeter kilograms divided by 1 centimeter kilograms. So the units would cancel out as well. Okay, so you would get this number, which is 1, and this is unitless. So you understood why this is unitless. Now we need to understand why this is normalized. Okay, since we are dividing by something that is of the same scale. Okay, So this product of standard deviations is of the same scale as this quantity. Okay, so see, this magnitude is same as this. Okay, so what this tells us, the reason I chose this example is that you understand that the scale is same. This won't be far off. Okay, this either would be so yeah, I mean, basically what you need to understand is that the number, this final output or this would lie somewhere between -1 to 1. Okay, because you're dividing by something that is of the same scale. Okay, and correct. So what this does is, this gives us the second term, which is normalized. Okay, now we need to pay attention. So let me write it once again. So -1 to 1. Okay, which means that it can be 0 as well. Okay, so -1 will indicate that the variables or two variables would have negative linear relationship between them. Value of 1 would indicate that the two variables would have a positive linear relationship between them. Okay, 0. Okay, what would 0 tell us? 0 would tell us that there is no linear relationship between the two variables. Okay, so remember, value of 0 is not telling you that the variables are not related. What it is telling you is that the variables are not related linearly. In a linear fashion, they are not related. Okay, linear, and then the what? No. Okay, so this is important, linear. Okay, so we are not talking about non-linear relationships when the value is -1 or 1 or anything but 0. Okay, between this range obviously, but when it is 0, we are talking about non-linear relationships. Okay, yeah, we are not saying that there is no relation. There can be relation, but it would be non-linear definitely if the value is 0. Okay, okay, now we talked about one more fact, that if we multiply it by a constant, right, what would happen? So let's talk about that thing in case of correlation as well. So if you multiply by a constant each uh, each variable, basically x or y, then what would happen is that that product would cancel out. So 5.3, then 5.3, just like the units, this would cancel out as well. Okay, so multiplying by a constant would not really affect the correlation, because this component, the denominator, the product of standard deviations, is of the same scale. Okay, and it also works with differences, right? And then it has a square, but it also has a square root, so effectively the quantity would come out same as above, and then they will cancel out together. Okay, okay, now the question comes, why only linear? Okay, why does correlation works with only linear relationships? Why not non-linear? The problem is that the ups and downs, okay, would cancel out. Okay, so let me explain, okay, with a simple like graph. Okay, so let's draw the graph of x square. Okay, so goes something like this. So this would be 0, this would actually touch on the origin, so this is 0. Okay, and let's say that if this value is -2 on x-axis, this is 2, then this would be 4, and this would be 4. Okay, so the thing is, if you see this example mathematically, so this is x, this is y, x bar, y bar. Okay, so -2, 0, 2, and then 4, 0, 4. Okay, so -2, -2, 4, so -2, 4. Okay, and then 2 is 4. Okay, and then 0 is 0, 0, 0. Okay, so if you only see the numerator here, okay, what is numerator, right? So 1 by 2 times, which is covariance, okay, -2 times 0 plus 2 times 0. Okay, so I mean, no brainer, it would give you 0. Okay, so this is the problem, right? Your term becomes 0, right? But you can clearly see that there is a relationship between x and y. Okay, but it is non-linear, right? So the problem here is that the formula of correlation would really fail to identify non-linear relationships. Okay, whether they are positive or negative, basically it would simply give you 0. Now the good thing, however, the good thing about correlation is that because it is normalized, okay, because it is normalized, -1 to 1, right, you can compare between different correlations. Okay, so for example, if you had data about height and weight, and then you had a data about height and age, right? So this would make a good comparison, right? So if you calculated correlation, you can say that the correlation between height and weight is let's say a positive number like 0.85, and the correlation between height and age is another positive number, let's say 0.75. So you can say that the relationship between height and weight varies linearly, positively, right? But in a better way as compared to the relationship between height and age, which is also linear and varies positively, but height and weight varies more positively, right? So you can say that you can actually compare, because because any correlation that you would find out would lie between -1 to 1, right? So you can compare, they are normalized and they follow same scale, okay, and are unitless. Okay. So let us take an example now. Okay. So you have data x, which is like hours studied, and then y, which is score in percentage. Okay. So 2 hours, 4 hours, 6 hours, 8 hours, and 10 hours. And this is 51%, 59%, 67%, 74%, and 80%. Okay. So correlation, if we calculate, and you can calculate this, I have already calculated. So correlation would something be like 0.998, right? It is positive and close to 1, okay, which is almost like perfect correlation, but almost, okay, not perfect. Okay, yeah. So let us understand why it is less than 1, or what does less than 1 signifies and what does 1 signify. So if it had been 1, it had been perfect correlation, wherein we could have said that if you increase the hours, number of hours you study, then you would definitely, or almost in 100% of the cases, would see that the score increases as well with respect to this data set. Okay, right? We are always talking about respect to a particular data set. This is not a general statement, but what we are saying is if the correlation had the value of 1, we could have said with 100% credibility that if you increase the number of hours studied, you would definitely, or 100% of the times, would see that the score increases as well. But this is not 1, this is 0.998. So what does this mean? Let us understand. Okay, why less than 1? So you can see that if you study 2 to 4 hours, okay, so 2 to 4 hours, the percentage score increases by 8%. Okay, if you study 4 to 6 hours, it increases by 8%, so this is consistent. But if you do 6 to 8 hours, okay, the percentage increase is 7%. So the inconsistency comes here, okay, which means that the gaps are not consistent, okay, not identical, okay, which means that the relationship is not perfectly linear. It doesn't increase like a line. So it would do 8 8 and then it would come to 7. Okay, so this breaks linearity. Okay, that is the reason it is not 1. If it had been perfectly 1, then it would be something like this, a straight line. Okay, 1 less than 1. Okay, so 8 to 10 hours, we again have plus 6%. Okay, so which means that there is another break here. Okay, yeah, something like this. All right, so you understand what does the value being less than 1 means. Okay, yeah, so what this also tells us that the correlation is a very sensitive measure. Okay, correlation is a sensitive measure, and if you think about it, it would be greatly affected by outliers. Greatly affected by outliers. Okay, and just as I mentioned earlier, right, that correlation can be used to compare between different data sets, different related data sets, basically, right? I mean, there is no point in comparing two different data sets which are completely unrelated to each other. Okay, so for example, in our case, what you can do is that you can collect the data from different classes studying same subject, and then compare correlation between studiers and marks to find out that which classes students get most return for the time they spend studying. Okay, so this is a very good application of correlation. Okay, now let us understand when to use. Can be used to check relationships between linear data. Okay, check relationships between linear data. Okay, so what you need to highlight is this linear. Okay, linear data. When not to use. Okay, not a measure of causation. We studied causation in the previous video, not a measure of causation. Okay, right? So again, not causation. These two are important words. Okay, and then doesn't tell you that X causes Y. Okay, so that is what we mean, right? Doesn't tell you that X causes Y. Causes is the important word here, which relates to causation. Okay, and then not. Okay, and when not to use, do not use in non-linear cases. Okay, all right, so that's it. Thank you for watching. Please like, share and subscribe. This will motivate me to create more videos. Simply hit that like button and the subscribe button for more such content. And yeah, let's see you in the next video. Thank you.